Assalamualaikum warahmatullahi wabarakatuh. Have a nice day. Today we will learn about momentum. Momentum, impulse, and conservation of momentum. As we know, momentum could be defined like this. This is equation for momentum. P is equal m times v. V is momentum, m is for mass, and v is for speed or velocity. Unit for momentum, if we have a international standard, use a kilogram meter per second. Momentum is like a vector because they have a value in the same direction. Total force is required to change of body momentum to move the particle. Momentum is directly proportional about both of mass and speed. Sometimes a big and slow some particle could have the same momentum with a small and fast particle. Now we discuss about momentum as a vector. If we draw a vector like this, momentum can be drawn like this equation because the momentum vector does not have to be drawn 10 times longer than the velocity vector. Since the only vector of the same quantity can be drawn on this way. Momentum can be drawn like this. If we have some particle with a mass 5 gram and speed 9 km per second, momentum will be calculated for equation P equal to m times v, and then momentum have a 45 kilogram meter per second and have direction 26 degree north of east, like this. This is a sample for equivalent momentum. If we have three vehicle, first is bus, second car, and third is train. Three but vehicles have different mass and different velocity. The train, bus, and car all have a different mass and speed, but their momentum are the same in magnitude. The massive train has a low speed, the low mass car has a great speed, and the bus has the moderate mass and speed. We can only say the magnitude of them are equal since they are moving in the same direction. The difficulty is bringing each vehicle to rest in terms of combination of the force and time required will be the same, since they each have the same momentum. For the more explanation, you can look at the video after this. Check it out.
In today's video, we're going to look at momentum, which is a property that all moving objects have. The main thing to know is that momentum is equal to the mass of an object multiplied by its velocity. So if we saw a 4,500 kilo dinosaur charging at 12 meters per second, then its momentum would be 4,500 times 12. So 54,000 kilogram meters per second. Whereas if we had a 1,200 kilo car traveling at 25 meters per second, then its momentum would be 1,200 times 25, so 30,000 kilogram meters per second. An important thing to remember though is that momentum is a vector quantity, so it has both a magnitude and a direction. So here, if we consider the forward direction to be to the right, then the dinosaur will have a positive momentum, but the car must have a negative momentum. The next thing to know is the conservation of momentum principle, which is the idea that in a closed system, the total momentum before an event, like a collision, is exactly the same as the total momentum after the event. To see how this works, let's imagine our dinosaur and our car as two particles, which are travelling towards each other and are going to collide, after which they'll both continue moving together at the same speed. How would we find their velocity after the collision? Well, the first thing we need to do is find their total momentum before the collision, which we can do by adding together the dinosaur's and the car's momentums. So 54,000 plus negative 30,000, which gives us positive 24,000 kilograms meters per second. Then, because of our conservation of momentum principle, we know that once they've collided, their total momentum must still be positive 24,000. And remember that in this scenario, a positive number means that it's going to the right. So after our particles collide together, they'll both get carried to the right, because the purple one had more momentum. And because they're both moving together, we can now treat them as a single large particle. So to work out their shared velocity, all we have to do is rearrange our momentum equation to show that velocity equals momentum divided by mass, and then plug in the values for this combined particle. So 24,000 divided by their combined masses from before, which would be 4,500 for the dinosaur plus 1,200 for the car, so 5,700 kilos, which gives us a velocity of 4.4 meters per second to the right. So basically, after the dinosaur and the car collide, they'd both continue moving to the right at a velocity of 4.4 meters per second. Now, in some circumstances, the momentum before an event might be zero, like it is for stationary objects, which don't have any momentum because they're not moving. And so in these cases, the total momentum after the event must also be zero. For example, if we imagine a gun before it's fired, then its initial momentum would be zero, because its velocity is zero. However, once the gun fires, the bullet that flies out will have a momentum in the forward direction. And so to compensate for this, the gun has to recoil backwards with an equal momentum, so that together the total momentum is still zero. So if we knew that this gun had a mass of 2 kilos, and that a 5-gram bullet was fired out at a velocity of 120 meters per second, we should be able to work out the velocity of the gun's recoil. The key to this is remembering that the gun's momentum plus the bullet's momentum must equal zero, because it started off at zero before the gun fired. The first thing we want to do is find the bullet's momentum using this bottom equation. So we do 0.005, which is its mass in kilos, times its velocity of 120, which will give us a momentum of 0.6 kilometers per second. Next, we want to try and find the gun's momentum. So again, we just do the mass of 2 times the velocity. But because we don't know what the velocity is yet, we can just write v for velocity. So the momentum will be 2v. where 2 is the mass in kilos, and v stands for the gun's velocity, which we're about to find out. Finally, we can use these momentum values for the gun and the bullet to rewrite our equation as 2v plus 0.6 equals 0. And then we can just rearrange this equation to find out the missing value of v. So first, we subtract 0.6 from both sides, giving us 2v equals negative 0.6, and then we divide both sides by 2, leaving us with v equals negative 0.3 meters per second, which is the gun's recoil velocity. And remember, the fact that it's negative means that it's effectively going backwards. Or in other words, it's going in the opposite direction to the bullet. The one thing we haven't mentioned yet is that you need to know that the letter symbol for momentum is rho, which looks like a P. So the momentum equation can also be written as P equals mv. In this video, we're going to look at how we can use forces to speed up or slow down an object, thus changing the object's momentum. We saw in the last video that momentum is equal to mass times velocity. So if we had a 2 kilo particle that was travelling at 5 meters per second, then its momentum would be 2 times 5. So 10 kilogram meters per second. If we then applied a force to it though, in the same direction as it was travelling, then that would cause it to accelerate and speed up. This increased velocity would mean that its momentum has also increased. For example, if it was now travelling at 8 meters per second, its new momentum would be 2 times 8, so 16 kilogram meters per second. To work out exactly how much force is required to cause this change in momentum, we need to use this equation, which says that the force is equal to the change in momentum divided by the time over which the change took place. So if we knew that the hand had applied the force over a period of 0.5 seconds, then to calculate the size of that force, we'd first of all need to work out the change in momentum, which would be 16, which is our final momentum, minus 10, which remember was the initial momentum of the object before it was hit. And this would give us a change in momentum of 6. And then we can just divide this change in momentum of 6 by the change in time of 0.5, and that would give us 12 newtons. So the hand must have applied a force of 12 newtons. Another way to write this equation is like this, where mv is the final momentum and mu is the initial momentum, because v and u are the final and initial velocities of the object. Let's now try another question using this new equation. Calculate the force required to accelerate a 600-gram ball from rest to 14 meters per second in just 0.1 seconds. So for questions like this, that involve quite a lot of different values, it's best to write out a list of everything that you know. So we could say that the initial velocity is 0, because the object started at rest. Its final velocity is 14. Its mass in kilos is 0.6. And the time is 0.1. Then all we have to do is plug all of these into our equation. So we get 0.6 times 14 for the mv part, minus 0.6 times 0 for the mu part, and then divide all of that by the time of 0.1. So if we simplify all of that, we get a final momentum of 8.4, minus an initial momentum of 0, all divided by 0.1, giving us a force of 84 newtons as our answer. Now, one area where this stuff is really important is during car crashes. If somebody travelling in a car collides with a brick wall, then their momentum is going to decrease to 0 almost instantly. This massive change in momentum means that any people inside the car will experience a huge force, which can cause injuries like head trauma or spinal damage. To reduce the chance of damage, we need to try and spread this change in momentum over a longer period of time, because this will reduce the force that they experience, and so they're less likely to get injured. In order to help them achieve this, cars have to, by law, be built with a bunch of different safety features, like crumple zones, seat belts, and airbags. Crumple zones are at the front and back of the car, and can crumple on impact, so that instead of stopping suddenly, there's a small amount of extra time for the car to lose momentum as it crumples. Seat belts, meanwhile, have two functions. One is to stop you from physically flying out of the car as it stops, but the other is that they're slightly stretchy, so that you slow down a bit more slowly. And finally, airbags also act to help you lose momentum more slowly. This is because they're compressible like a pillow, unlike the hard dashboard or steering wheel that you might hit otherwise. Lots of other safety systems work in a similar way, for example, helmets or crash mats. The key thing to remember is that all of these increase the time it takes for the momentum to be lost, which results in a lower force acting on the person, and so reduces the risk of harm.
Now we will learn about impulse. Impulse could be defined like this. Impulse is defined as the product force acting on an object and the time during which the force acts. The symbol of impulse is J. This is equation for impulse. J equal to F times T. J is simple, F is force, T is time. For example, if we have a 50 Newton force applied to 100 kg of boulder for 3 seconds, the impulse can be calculated like this. J is equal 50 Newton times 3 seconds, and the result is 150 Newton second. Impulse unit. As for the equation, show why the standard international unit for impulse is a Newton second. There is have a same unit for momentum. We can prove it. 1 Newton second is equal 1 kilogram meter per second quadrat times second. And equal is 1 kilogram meter per second. As you know, kilogram per meter second quadrat is equal as a Newton law conversion. F naught equal to m sum a. We know that a is acceleration for equivalent to a Newton. Therefore, impulse and momentum have the same unit, which leads to the useful theorem. The impulse due to all force acting on an object, the net force, is equal to change momentum of the object. Look at the equation. F net or force c is equal delta p, or change of momentum. We know the unit of both sides have the same equation, but let's prove the theorem normally. Look at the equation. F naught times t is equal m times a times c, and then equal for m times delta v, or change velocity, and then equal delta p, or momentum change of momentum. Now for a sample for momentum and impulse for stopping time. You can look this illustration. This is a car wheel hitting the wall. This is a car wheel hitting the high shaft. Imagine a car hitting the wall and coming to rest. The force on the car due to the wall is large, or a big F, but the force only acts for a small amount of time, or small t, or little t. Now imagine the same car moving at the same speed, but this time hitting a giant high shaft like this and coming to rest. The force on the car is much smaller now, or a small f like this, but it is act for a much longer time, or big T. In its case, the impulse involves the same scene. The change in momentum of the car is the same. Any net force, no matter how small, can bring an object to rest if it has enough time. This is a sample connection between impulse and momentum. If we have a 1.3 kilogram force coming strike at 75 kilogram shock applier with speed 13 meters per second, who kicks in the exact opposite direction at 22 meters per second with average force of 1200 Newton. How long are his foot and the ball is contact? We can use this equation. Since the ball changes direction, we can use delta p equal to m times of delta v, and then we can calculate for this equation, and the result is 0.0379 seconds. This is time his foot and the ball in contact. During this contact, time the ball compresses substantially and then decompresses. Now we learn about conservation of momentum in one direction. Whenever two objects collide, or when they are exert force on each other with their colliding, such gravity, momentum is conserved. This means the total momentum of the object is the same before and after collision or crash. Before crash, momentum have equation P equal to m1 times v1 minus m2 times v2. Cosine right as the positive direction, m2 has a negative momentum, like this. After crash or collision, the equation change like this. P equal to negative M1 times VA plus M2 times VB. After crash, the particle have different direction before correction or crash. Direction after collision. One the last slide, the box was drawing going to opposite direction after colliding. This is always the case. For example, when the bat hits the ball changes direction, but the bat doesn't. It doesn't really matter. So, which way we draw the velocity vector? In after of this, if we solve the conservation of momentum equation for VB and got a negative answer, it will mean that M2 was still moving to the left after the collision or crashing. As long as we interpret our answer correctly, it's a matter now how the velocity vector are drawn. Now look at a sample problem. A rifle fire a bullet into a giant slab of butter on a frictionless surface. The bullet penetrates the butter, but while passing through it, the bullet pushes the butter to the left, and the butter pushes the bullet just a hair to the right, slowing the bullet down. If the butter skids off at about 4 cm per second after the bullet passes through it, what is the final speed of the bullet? This is the answer. Before we calculate the answer, let's cause left to be the positive direction and use conservation of momentum, converting all units to meter and kilogram. And now we calculate momentum before crash. We can calculate that, and the result is 25.5 kilogram meter per second. Now we calculate momentum after the crash. After the crash, we have the new equation. Momentum is equal to 0.28 plus 0.035 for speed, time speed, and then we can calculate for momentum before crash and momentum after crash, like this. And then we have a result for speed. A bullet after crash is 692 meters per second. After we learned about the sample before, for calculate sample before, now we will approve of conservation of momentum. We can look this illustration. The proof is based on Newton's third law. Whenever two objects like this for collide or crash or exert force on each other from a distance, the force involved on action and reaction. Action and reaction were equal in strength, opposite in direction. This means the net force on the system, the two objects together, is zero, since this force cancel out, like this. For each object, F for mass, A is acceleration equal for mass times delta V over T, N is equal delta P per delta T. Delta P is momentum, T is time. Since the force applied to the contact time is the same for its mass, the H undergo the same change in momentum, but have opposite direction. The result is that even though the momentum of individual objects change, delta V for the system is 0. The momentum then that one mass gain, the other losses, hence the momentum of the system before equal the momentum of the same after. Okay, that's all for me about the momentum problem. If any question, don't hesitate to ask me. Thank you very much. Waalaikumsalam warahmatullahi wabarakatuh.